Welcome to video number 3 in our series on gas laws. Remember, we've already seen video 1 and done practice on gas properties, and video 2, which is practice using the ideal gas law, PV equals nRT. Today we're going to look at one more gas law. Is Graham's law of diffusion. Graham's law of diffusion is very useful and also very interesting. So remember, diffusion of a gas is the ability of a gas to mix and spread, where effusion of a gas is any gas leaking out of a tiny hole. So any tiny hole a particle could fit through would be effusion. Any diffusion of a gas, if I open the container, the gas will leak out and diffuse into a large cloud. The kind of cloud that might drift over a town if there is a chemical spill. Gases diffuse into large clouds since the particles are always moving. Or gases effuse out of any tiny hole that the particle could fit through. And this is why balloons lose pressure. You have a balloon at noon on one day, and the next morning at 6 a.m. your balloon is smaller than it was because some of the gas particles inside the balloon effused out of the tiny holes in the latex material. Diffusion and effusion both use Graham's law of diffusion. So for Graham's law of diffusion, we're going to construct the way the formula works, okay? All right, let's go through this derivation. Let's say I have two gases at the same Kelvin temperature, two samples of a gas. And they're both at room temperature, or maybe they're both at standard temperature. They both have the same Kelvin temperature. That will mean that their particles have the same average kinetic energy, right? Because temperature is a measure of the average kinetic energy of a sample's particles. If we look at the definition of kinetic energy, the kinetic energy of a particle is 1/2 mv squared. And m is the mass of those particles, and v is the velocity of the particles squared. Kinetic energy is 1/2 mv squared. So because they're at equal Kelvin temperatures, the kinetic energy of the particles in gas 1 will be equal to the kinetic energy of particles in gas 2. Same Kelvin temperature, same average kinetic energy. That means 1/2 m1 v1 squared is going to be equal to 1/2 m2 v2 squared. I just substituted in the kinetic energy formula. Well, now let me rearrange the equation. And now if I divide both sides by m2, I get this, m1 v1 squared over m2 equals v2 squared. And now I'll go even further. m1 over m2 is going to equal v2 squared over v1 squared. Taking the square root of both sides, I'll end up with Graham's law of diffusion. The square root of the quotient m1 divided by m2 will be equal to the ratio of v2 over v1. Remember, this is the ratio of the velocities of the particles, and this is the ratio of the gas masses. The mass of the first gas and the mass of the second gas. And the great thing in applying Graham's law is these velocities can also be the rates of movement. So if we know the rate of diffusion, we can use that in this or this. If we know both rates, we can plug them both in. If we know one rate, we can plug one in. And for the ratio of gas masses, these can be molar masses. So we can, if we know the molar mass of the first gas and the molar mass of the second gas, we can take the square root of their ratio and figure out the rate of movement. So Graham's law of diffusion is quite a useful formula for us. I want to try an example problem. So we're going to do a few example problems where we're going to apply Graham's law of diffusion. So let's read it. Equal amounts of helium and argon are kept in a porous container. Well, that means we're going to see effusion. The question is, which will escape faster? Equal amounts of helium and argon are kept in a container. Which one do you think is going to escape faster? They've got to escape through any tiny holes. So the first to escape is going to be the tinier gas. So that's a little bit intuitive, but that's going to be helium. And you'd be correct. Being the smaller atom, the smaller gas particle size, helium will escape faster. But how much faster? In order to do this, we're going to have to use Graham's law of diffusion. But we've got the molar masses, and we've got some information about rates. Well, here's what I'm going to do. I'm going to call the rate of argon 1 and the rate of helium x. Then I'll be able to tell whether helium is 2 times as fast or 0.5 times as fast. What's my expectation? That helium will be faster than argon. So it's a nice little trick to set the rate of the argon's diffusion, or in this case, effusion, out of the container, set the rate of argon's effusion to 1, and then calculate the rate of helium versus argon, and we'll get a ratio. Here's what else we know. The molar mass of argon from the periodic table is 39.95. The molar mass of helium is 4.00. So now let's use Graham's law of diffusion. I'm going to write the rate of 1 over the rate of 2 is going to equal the square root of the molar mass of 2 over the molar mass of 1. All right? So that means I'm going to let helium be gas 1. X over 1 is going to equal the square root of 39.95 over 4.00. Well, that's just basically the square root of 10. 40 divided by 4 is 10. So x over 1 is going to equal 3.16. That's the rate of helium relative to argon. So how much faster will helium effuse? 3.16 times the rate of argon. So if the question asks you about how much faster, then you can use this, set one of the rates equal to 1 and the other rate equal to x, and then solve for x. Let's try a little more complicated problem, the second example problem, which involves Graham's law of diffusion. Here we're going to do example 2. So let's read this problem. At standard temperature and pressure, STP, the density of hydrogen gas is 0.090 grams per liter, and the rate of its diffusion is 5.93 times the rate for chlorine gas. Determine the density of chlorine. Determine Cl2 gas's density. Well, I can tell right now, because I've done a lot of these, that this is going to be a combination problem. The units of chlorine's density is going to be grams per liter. It's going to be mass over volume. And they've given me this hint at STP. So whenever I see STP, I think I might want to remember the molar volume of a gas. From video 1, 22.4 liters will equal the volume of 1 mole of gas. If we're at STP. So I'm just going to keep this in mind. I'm also going to keep Graham's law of diffusion. So I'm probably going to do a combination of this and this to solve this problem. So in order for me to solve this problem, I'm going to have to need some rates. And I have information for rates. So I'm going to set the rate for the diffusion of chlorine to be equal to 1. Then the rate for hydrogen will be 5.93 times that. So I can set that to 5.93. Great, I've got those two numbers. Now in Graham's law of diffusion, I will use mass of one over mass of the second, but I can also use molar mass. And it's going to be really easy for me to figure out the molar mass of hydrogen. So what's the molar mass of hydrogen? It's 1.008, and that's times 2. So I'm going to call that 2.02 grams per mole. So I have all the things I need to do. I'm going to fill them in the Graham's law of diffusion equation. So I'm going to do R1 over R2. That means 5.93 over 1 is going to be equal to the square root of the molar mass. So this is going to be whatever the molar mass of chlorine is divided by 2.02. This way I'm using the data given to me in the problem to solve. Now what will I do with this square root? I'm going to have to square both sides of this equation to get this to work. So when I square both sides of that equation and let the molar mass of Cl2 be x, when I solve for x, I get 71.03 grams per mole. That makes me feel pretty good because that's about double what Cl is on the periodic table. Am I finished? Does this answer the problem? This is molar mass. This is a combo problem, and I'm trying to get to grams per liter, density. So let me take this 71.03 grams per mole and use the molar volume of any gas, 22.4 liters for every 1 mole, and make a ratio that will cancel the units of moles and get me into grams per liter, which will be density. And when I do that division problem, 71.03 divided by 22.4, I get 3.169 grams per liter. There you have it. That's about as complicated as it gets. Using Graham's law of diffusion to find a molar mass of an unknown gas. And then using the molar mass with the molar volume at STP and finding the density. I'm going to let you finish the practice problems I'm left for you and also direct you to the work study book, page 132 and on, for all those chapter 5 problems you can practice with their solutions right there. Thanks for listening. Good luck.